Okay, so does anybody want to tell me about this? A is invertible if and only if the columns are linearly independent. Julia, yeah?
I said I don't remember the proof exactly.
That's all right. That's
one
good.
of the things that we said about invertibility is that in a system A times the matrix X, it will always equal the zero matrix, or zero vector, I guess. So if you have A, it will be AX equals 0.
Yeah, so invertibility is equivalent to something about this system, right? So you're invertible if and only if what happens? If and only if the only answer to this is when x is equal to 0, the zero vector. And this has one solution only, one and only one. Right, namely x equals 0. Right, so the only solution to this is x equals 0. Right, and that's it. That's basically that's the connection. Right, why is this connected to linear the independence of the columns? Can anybody spell it out? Yeah, Lizzie.
Sorry, this might be totally wrong, but does it have something to do with the fact that the determinant of A equals the determinant of the transpose of A at all?
You don't need to go that way. Okay. You don't need to go that way. So that way would be if you wanted to say that the rows are linearly independent.
Okay.
But so you don't need to go that way.
Okay.
Molly, did you want to say?
Yeah, so what we talked about last lecture was essentially that if they're not linearly independent, you can use two column vectors to cancel each other out and form the zero vector, which would mean that there's a set of x being a vector that would not be 0.
Okay, so you're saying, well, look, linear dependence is the same thing as saying that there's some way of getting there's some way of combining the vectors and getting the zero vector where not all Ci are 0. Right? There's some non-trivial way of getting the zero vector. Right? So there's a non-trivial combination. There's a non-trivial combination of the vectors that gives you the zero vector, right? But that's the same thing as saying that this has multiple solutions, right? That's the same thing as saying that this has multiple solutions. Let me be a little less sloppy about it. So you say, okay, well, A invertible is the same thing as saying that this has one solution only, right? But that's the same thing as saying, remember what this is. This thing here is the same thing as x1 a1 plus x2 a2 plus xn an. Right? This thing here, remember, when you take a matrix and multiply it by a vector, that's the same thing as taking the entries in the vector and multiplying the columns by it. Right? So this is the same thing as saying that this has one solution only, namely x1, namely take all the xi's to be 0. Right? But that's linear dependence. That's linear dependence, right? Linear dependence is there only one way to get the zero vector? And this is saying, yeah, there's only one way to get the zero vector. So it's exactly the same thing. Okay, so just to remind you where we were last time. Any questions about that? Okay, I hope that's completely clear. Right? The main trick is what we call the key observation at the beginning. Right? We said at the beginning of the class ages ago that when you multiply a vector, then that's the same thing multiply a vector by a matrix, that's the same thing as multiplying by the columns by the entries of the vector, right, and adding them together. Okay, so that was the key observation, and you see that we use it again and again. Okay, okay. Well, let's go on to the next section, which is called basis and dimension. Basis and dimension. Okay, so here's what we want to do. So observe. If we can find a spanning set wait, I should first say, given a vector space V. So you start off with some vector space. Okay, it's an abstract vector space, doesn't have any coordinate system on it. If we can find a spanning set, Vi of V, that is also linearly independent. Okay. If it's also linearly independent, then we have something good, right? Then everybody, each vector in the vector space corresponds to a unique linear combination. Right? Corresponds to a unique linear combination of the VI. Everybody remember that, right? The good thing about linear independence was that everybody in the span had a unique linear combination corresponding to it, right? You guys have to write faster. Write faster. Okay, right. The good thing about linear independence was that everybody in the span corresponded to a unique linear combination, right? There was only one way to express it. Okay. So if you have a vector space and you have a set that spans the whole vector space and it's also linearly independent, then everybody in the vector space will correspond to a unique linear combination, right? Okay. So what's good about that, right? Well, what would be good about that is that then you can associate to each vector the coefficients of that linear combination, right? You can associate to each vector a set of unique coefficients, right? And those are like a coordinate system for your abstract vector space. Okay, so the above basically gives you a coordinate system for your abstract vector space V. Okay, so your vector space didn't start out with a coordinate system, but if you can find a spanning set that's also linearly independent, then you can put a coordinate system on it. Okay, and that's a good thing. Okay, so this leads us to the definition of this desirable thing, which we call a basis. So if you have a set that does two things. This set Vi from I equals 1 to n spans the vector space V, and 2, so again V is a vector space. If you have a set, so the Vi are vectors in the vector space. If your set spans the whole space and is linearly independent, then we call this Vi thing a basis V. A basis of V. So let me just give some examples. Maybe the simplest example is, suppose we're in R2, right? What's sort of the natural basis of R2? Suppose we're in R2. What's a sort of obvious basis of R2? Avid?
+1 and -1.
So we're in R2. We're in R2.
Sorry, 1, 0, and 0,
Yes.
and 0, 1.
That's right. Okay. So we could take our V1 to be 1, 0. This guy here, right? And V2 to be 0, 1. Right? This guy here, right? Then these guys, their span is the whole space, and they're linearly independent. Okay? So these guys are a basis for R2. Okay? Right? If we look at, say, P3, remember P3 is the polynomials of degree less than 2. Sorry, polynomials, I'm sorry, less than 3, of degree less than 3. What's sort of the natural basis for P3? Avery?
Would it be 1, 0, 0, and 0, 0?
So these are polynomials, right? So polynomials, things that look like, x plus x squared plus 5 or something like that, right? So like, how do you make, what are three polynomials whose combinations give you everything in this space? Anybody? Other than Reed? Reed is banned from speaking? No. That's good. Anybody else? Molly? No? Dan? Reed?
Squared x and 1.
Sure, right? So, right, the polynomials, right, you take one polynomial being x, 1, another polynomial being x, another polynomial being x squared. Okay? And everybody in the space can be expressed as a combination of these three polynomials. Right? And we saw last time, I think we saw last time, that these polynomials are linearly independent. Right? So these three polynomials, and people usually abbreviate it just 1x, x squared. Those three polynomials, 1, x, and x squared, are basis, okay, of P3. Okay, is that okay? Okay. Another example, more sophisticated, slightly more sophisticated. Recall, we did a null space, right? We calculated the null space of the matrix 1, 0, 5, -3, 0, 1, 2, -1. Turned out to be the span of two vectors, -5, -2, 1, 0, and 3, 1, 0, 1. We did this example when we introduced the null space. Okay. Now, look at these vectors. Are they linearly independent? Are they linearly independent? Are they dependent, say? Is this guy a multiple of that guy? No, right? Impossible, right? We can't multiply this guy and get to that guy, right? Because to get the 0 here, you'd have to multiply this whole thing by 0. Well, that would give you 0. Okay, so they're not linearly dependent; they're linearly independent. Okay, so these are it's a spanning set, obviously. It's clearly a spanning set, and these guys are linearly independent. So this is this thing here is actually a basis for the subspace and A. Okay, everybody all right? Anybody confused? I should ask if anybody's not all right, rather than if everybody's all right. Okay, I hope everybody's getting a sense of what a basis is. Okay, basis is a bunch of vectors. You have a vector space. You have a bunch of vectors in your vector space that are linearly independent and whose span is the whole vector space. Okay, so that leads us to our second definition, something called dimension. Okay, so V, a vector space again, and suppose that Vi is a basis. Basis of V, a basis for V. Okay. Then the dimension of V, the dimension of the vector space is defined as, so usually we write a dim V, is defined as the number of elements in the basis. Okay. This symbol here, number, we use as, you say, the number of elements in the set. Okay. So the number of elements in the set. So the dimension is defined to be the number of elements in a basis. Okay, so for example, coming back to here, right, what's the dimension of R2? Well, we say the dimension is 2 because you got a basis with two elements. P3, what's its dimension? It'll be 3 because we found a basis with 3 elements, right? What's the dimension of the null space here? Well, it's 2, right? The dimension is a 2-dimensional subspace. Okay. Okay. So that's how we define dimension, right, for vector spaces. You find a basis, and then just count the number of elements in the basis. Yeah,
And then being linearly independent ensures that we have the minimum number of vectors.
Right. So you actually, that's great, Reed. You're catching on to some problem with this definition. So there's a problem with this definition, which is that how do you know that all bases have the same number of elements? Right? There's nothing here that says all bases are gonna, if you have a vector space, you're always gonna end up with the same numbers in a basis. Okay, so we actually have to prove that. So yeah, there's something wrong with this definition. Okay, we'll deal with it in a second. I'm always reminded at this point of a college classmate of mine who was really, really strong in mathematics. He was taking a physics class, and the physicist had introduced some vector space that was infinite dimensional. Okay, and he had one basis for it, and then he said, okay, now we're going to switch to this other basis. Okay, but at this point, my friend stood up and started shouting at the professor, saying that he'd made a mistake because the first infinity was a different size infinity than the other infinity. That is, the first basis had infinitely many elements, the second had infinitely many elements, but they're actually different. One infinity is actually strictly larger than the other infinity. And so he's saying, like, what are you saying about this space? Okay, yeah, we can talk about that at some point. But anyway, with finite dimensional vector spaces, we don't have to worry. We're not going to do anything crazy. Okay. So yeah, there's a problem, which is that how do we know all bases of the vector space, have the same number of elements? Okay, and we'll sort of address this problem with the following theorem. Okay, so here it is. suppose that V1 through Vn spans a vector space V. Okay, suppose you have some elements. Suppose you have a spanning set of V. If m is a number strictly bigger than n, then any set of vectors u1 through um must be linearly dependent. Any set of vectors that has more vectors than the spanning set. If you have more vectors than the spanning set, then you must be dependent. If you have more vectors than a spanning set, you must be dependent. Or another way of saying that is that the size of an independent set must be less than or equal to the size of a spanning set. Because if you take the contrapositive, it says that if u1 through um is linearly independent, then m must be less than or equal to n. Right? Then they must have fewer elements than the spanning set. Yes, Ian.
How can they ever be equal? Like, how can the number of elements in an independent set ever be equal to the number of elements in a spanning dependent set?
How could I'm saying? Let me
say that the number of vectors in the independent set must be less than or equal to the number of elements in the
spanning set.
So in dependent set.
So for example, here's an independent set, right? It has two elements. But a spanning set in R2 would also have two elements, right? If it's
the spanning set doesn't
that's the dependent set. The linear dependent.
Okay, yeah. So you just misread it. That's okay. Okay, so are people okay with this statement? Right? It says if you have a spanning set and you have a bunch of vectors, there are more vectors, you have a set of vectors whose number is greater than that of the spanning set, then these guys must be linearly dependent. Okay, or contrapositive, if you're independent, then the size must be less than or equal to the size of the spanning set. This thing is also called cardinality. Cardinality basically just means the number of elements in the set, aka the cardinality of the basis. Okay, so in terms of like a picture, right? Here you have in R2, here's a spanning set, right? Here's a spanning set for it, right? It has two elements. If I have more than two elements, if I have another set, so these are my V's, V1, V2. If I have three guys in this space, This is saying that if you have 3 guys in the space, they must be dependent. Okay. So whenever you have a set whose cardinality is bigger than that of a spanning set, then there must be some dependence between them. Okay. And that's what this theorem is saying. Okay. Okay. The proof of this, I have to say, is not sort of really exciting, but let's do it anyway. I'm always tempted to skip this proof, but I think you should probably see it. You know, not everything in math has to be exciting. I guess that must be kind of a strange statement to you. Not everything in math has to be exciting. You're all thinking like, what does he mean? Like everything in math is boring, or and maybe you're all like thinking the completely opposite way. But I'm like, no, not everything is exciting. There are some boring things. There are some few boring things. This is one of them, I think. Okay, so yeah, I hope that made sense. That statement actually made sense to you. And you weren't like, what? Okay, so let's start off, right? Okay, suppose we have a bunch of vectors in V, and suppose we have these guys whose cardinality is bigger. Okay, so we want to show that the ui, I from 1 to m, are linearly dependent. And I'm hoping that you all are not actually bored, but just tired. So we want to show that these guys are linearly dependent. In other words, we want to find, we want coefficients C1 hat through Cm hat, not all 0, such that Ci hat ui from I equals 1 to m is the 0 vector. Right? We want to show these guys are linearly dependent, right? And that's what that means, right? That you can find a non-trivial way of getting the 0 vector. Okay. And what we'll do is show that it's theoretically possible to do that. Okay. With that, we're guaranteed a way of doing that. We can do it. We can do that. Why? Okay, well, you think each of the each of the ui is some linear combination of the v's, of the vi's, right? Because the vi are a spanning set. Right? Each of the ui is a linear combination of the vi's. So let's write it down. J equals 1 to n. Right? Each of the ui's is a linear combination of the vi's. Right? Because the vi's span the space. Okay. So let's write it here. So if we consider summation CIUI, we consider summation CIUI from I equals 1 to m. Well, that's the same thing as saying summation CI of the UI, but each of the UIs is expressible in terms of the VIs. Right. So I equals 1 to m, j equals 1 to n. Okay, and now I'm just going to rewrite that. I'm going to change the order. For the j, I'm going to sum over j's first, and then I'm going to sum over the i's next. So I get, I'm going to put everything together, aij, ci, dj. Now look at this sum here, right? The j goes from 1 to n, right? And the vj is, I can pull this vj out because it doesn't depend on the I, right? It's the same vj, it's just like vj gets multiplied by the same thing. So I don't have to include that in the I summation. I can pull it out, right? By distribution, right? By distributive property. So I distribute the vj out. Okay, and now, now observe that the system summation aij cj equals 0, equals 1 to m, j from 1 to n, is a homogeneous system with m unknowns and equations. Okay, so what am I going to say? What's the relation between m and n? M is bigger than n, right? So what? You've got a homogeneous system. You've got more equations than unknowns. Sorry, you've got more unknowns than equations. So, Adrian?
It's underdetermined.
It's underdetermined, and so.
Likely inconsistent.
Well, it's a homogeneous.
Oh, infinite.
So you've got infinitely many. You're guaranteed infinitely many solutions. Yeah. So there are infinitely many ways, many solutions. In other words, we can definitely find non-trivial aij that make these guys 0 all the time. I'm sorry, we can definitely find non-zero cj, that make all these guys 0. Okay, and that makes it equal to 0. So, right. So we can find the CI we were looking for. Right. So choose a non-trivial solution. That's the CI hat we wanted. There's infinitely many solutions, so there's definitely one. It's definitely one that's not just all zeros. Any questions? Any questions? No? Okay, let's go on then. So, okay, so let me show you how this is used. So what you see here is that here's what we've just shown. That if you have a linearly independent set, then its cardinality must be less than or equal to that of a spanning set. Okay, so now we say, okay, now, so it's corollary. Let V be a vector space. And suppose that V1, Vn is a basis. And suppose that U1, Um is also. Okay, suppose you have two bases. And suppose you have two bases of V. Then M and N must be equal to each other. Does anybody see how that follows from this statement, what we just proved? That if you have a linearly independent set, its cardinality must be less than or equal to that of a spanning set. Molly, go ahead.
No.
You don't? You're not? Okay. Okay, I want everybody to think about it for a minute and see if you can figure it out. Right? You know that an independent set, the size of an independent set must be less than or equal to the size of a spanning set. Why does that imply that if you have two bases, then they must have the same cardinality? You can definitely do it. So I'm going to walk around outside.
I mean, you mentioned basis means
Basis is just
expands the
I think it's just
and so you're
just like expressing it.
Okay, anybody figure it out? Anybody have an idea? How about you?
No.
No? Okay. What?
Said someone other than me.
Somebody other than Reed? I'll give 2 points in the exam to anybody other than Reed. No, that wouldn't be fair. Yeah. I take that back.
Yeah.
Okay, so yes.
So since they're both spanning sets and independent sets,
Exactly.
so N must be less than equal to M and M must less than be less than equal to N.
Right.
So the only thing that follows is they're equal.
Exactly. Right. So you say, well, look, right. If you're a basis, then you're linearly independent, and you're also a spanning set, right? Right. So this guy's independent and spanning. This guy is also independent and spanning. And so you say, oh, look, this guy is independent and this guy is spanning, right? So N must be less than or equal to M, right? Because this independent, we said that the size of any independent set must be less than or equal to that of a spanning set, right? So this N must be less than or equal to M, right? But, the other way around, this guy is independent and that guy's spanning. So we also know that M is less than or equal to N, right? And so that means that M and N must be equal. Lizzie, you're frowning. You don't like it.
No, it's fine.
It was too easy, right? Maybe. Yeah. We overcomplicated things. Okay. Okay. So let's. Okay. So that answers our problem, right? The basis always has to have the same number of elements. Like you can't. It's not going to be that you get one basis and it has 5 elements and another basis has 6. That's impossible. Okay. Right. So the dimension actually is well defined, right? When you choose a basis, it will give you a number, and no other basis is going to give you some other number. Right. Okay. Okay. So okay. So there's a couple other theorems in this section. One goes like this. Let V be a vector space. And suppose you know the dimension already. Suppose you know that the dimension of V is n. if V1 through Vn is a set of vectors, a set of vectors in V, then the set is linearly independent if and only if it's a spanning set. Okay. Okay, so what this is saying is that if you know the dimension already, okay, you have a vector space and you know what its dimension is already, okay, and you have a set with that many elements, then the set is linearly independent if and only if it's a spanning set. In other words, if it's linearly independent, it's going to be a spanning set. If it's a spanning set, they must be linearly independent. Okay, if you know the dimension of the space already. Okay. So what this is saying is that if you know the dimension already, you don't have to check both conditions to find a basis, right? If you know the dimension already and you have a set of that size and they're linearly independent, you automatically know it's spanning and so it's a basis, right? You don't have to check it's independent and spanning. Checking one of them implies each of them implies the other. Okay, so if you know the size already and you have a set of that size, then each of these conditions is equivalent to the other. Okay, you only have to check one of them. Okay, so let's think about that. Say that the VI are linearly independent, I from 1 to n are linearly independent, but they're not spanning. Okay, suppose they're not spanning, then what would happen? Okay, what would happen? Why does that lead to a contradiction? So what is this proof by contradiction? Proof by contradiction. Suppose you have a linearly independent set and they're not spanning. So in other words, their span doesn't cover the whole vector space. The span doesn't cover the whole vector space. There's somebody, so there exists some vector, Vn plus 1, that is it's in the vector space, but it's not in the span of the VI. It's not in the span of the other guys. Why is that impossible? This guy is in the vector space. It's not in the span. Lizzie, yeah.
Because then it would be linearly dependent. This guy and these guys would be linearly independent, actually, right? Because these guys are linearly independent to begin with, right. And then this guy wasn't in the span, so when you throw him in, he's also linearly independent, right? Julie?
Part of the definition of a span is that it's the set of all linear combinations, right?
Yeah.
So if there's a vector or if it's linearly independent but not how is it possible that it's like, I don't know. How is it possible that it's not a part of the linear combinations, but I don't know.
Okay. So let me, since we're running on negative time,
So think like this. These guys are suppose these guys are linearly independent, but not spanning. Then there's somebody who's not in their span, right? There's somebody who's not in their span, but then these guys, V1 to Vn plus 1, are linearly independent. You've got n plus 1 vectors who are linearly independent, right? That's a problem because you know that the dimension of your space is n, right? So there's a spanning set of size n, but you have a linearly independent set of size n plus 1. That's impossible, right? Because the spanning set should be smaller. The independent set should be smaller than the spanning set. Okay. So, but the dimension of V is n, which means that n plus 1, being linearly independent, must be less than or equal to n. Right? This is the size of the linearly independent set, and this is the size of the spanning set. Right, but that's false, of course. Right? N plus 1 is not less than 1. Okay, and then the opposite direction is kind of the same. Okay, let's stop here for today.